All right, podcast 1.3. We get to start actually talking about the different types of matter and some of their properties. And it's kind of a long podcast. Keep in mind, in class today, or last class, you should have filled in this top section of page 5 here. So our podcast actually starts right there in the middle of page 5, finishes out those couple of questions there pretty quickly, and goes through all of page 6, and then, don't kill me, it also does pages 7 and 8. But as you see, page 8 is just completely blank other than asking you to draw the matter flow chart. So we're going to go through all of these different types of matter and learn about how they're the same and different. And then that last page, page 8, is going to help us kind of divide up and relate them together all in one kind of image. So hopefully it's not too much. Do it in chunks if it does feel like a lot. But let's get going. I'm going to start by listing and defining our common states of matter. Solid, liquid, and gas are our 3 most common states of matter, but I do want you to squeeze in aqueous down there, and you'll understand in just a minute. Now, we've listed, let's define. Definition of a solid is that it has definite shape and volume. It means that the shape and the volume do not change, and that's because the molecules can't move. They're just sitting there vibrating in a set place, so that means that they can't spread out and change its volume or its shape. Liquids have indefinite shape, means that that shape can change definite volume. Molecules can flow and move around each other. Gases have indefinite shape and volume because the molecules aren't attracted to each other. They're completely free flowing, free roaming. They can expand to fill any size container that you release them into. Now, gases are also commonly referred to as vapor. I think that's kind of a little sub-question right underneath this section. So go ahead and write gases down there, or aka vapor right here. Now, aqueous. Aqueous is a little bit weird. Aqueous is a solid that's been dissolved in water, and it's not really a true state of matter, but when we study chemical reactions, we're going to be putting these little symbols, S, L, and G for solid, liquid, and gas, but you're also going to see AQ for aqueous. It is different than being a liquid. Even though it lets that substance act like a liquid, that solid has been dissolved in water, and the water is what lets it flow and move. A true liquid has started off as a solid maybe, and you've heated it up, melted it to turn it into a liquid. And there's slightly different properties and reactivity based on that, but a lot easier just to dissolve things in water than to melt them. So, those are our states of matter that I want you to be aware of. Now we're going to draw what they look like. You can just use some little circles to represent the model of the particles. And as a solid, those circles should be really close together and in kind of a regular repeating shape. I just kind of did 2 rows where they were really closely packed. These liquid molecules are a little bit farther apart, and you can see they're kind of randomly spaced. Some are closer, some are farther, but they're still kind of in one area. And then the gases have gotten as far away from each other as they can. Most of them are trying to escape this box, and we imagine they're going to be moving fast as well. So, all of these things that we talked about on page 7, that you're going to be filling in on page 7, is physical properties. Now let's talk about chemical properties, and these are properties that relate to how a substance can change into a new substance. Instead of just describing their physical appearance or the outer appearance like a physical change is, this is something that's kind of intrinsic to that substance and how it can act. So, just like I just said, physical properties describe what something is, chemical properties describe how it can change and kind of what it can be. Now, examples of each, they might sound very similar. I could say something like sodium is a soft metal. And that's what it is. That is a physical property. Or I could say sodium is reacting with water. That's talking about what it's doing and how it's changing. Even though I said sodium is, it's talking about a change and talking about a reaction. So that's going to be a chemical property. Saying water reacts with sodium to make sodium hydroxide. Chemical property. Or our water is formed from hydrogen and oxygen. Chemical property. This is talking about how it's formed, what it's made of. So, we're going to keep talking about this physical and chemical stuff and talk more about the changes, because properties describe what could happen, changes are talking about what is happening and changing. So, physical changes are processes that alter the outer appearance. Note that it does not change what it's made of. It does not change the composition. Chemical changes, on the other hand, are where one or more substances change into new substances. And that's the key difference between physical and chemical changes. We have to have a new substance when it's a chemical change. But how can you tell that there is a new substance there? How do I know when I'm looking at a beaker or a reaction if there is a new substance? Well, we're going to make a little list off to the side. Hopefully you have some space right next to these definitions. If not, you can probably make some space down below the examples we're going to be classifying of what are the indicators of a chemical change. These are our big neon signs saying, hey, a chemical change has happened. These are signs that a new substance has been formed. First one is bubbles. That's a new gas being made. And keep an eye out for bubbles. Precipitate or solid being made. Same type of ideas. New surprise solid out of nowhere. You're going to be very familiar with that word precipitate by the end of the semester. So let's start getting to know it now. Heat or light being released, also known as energy being released of some sort, any type. And color change. Now, all of these need to be surprise changes. If you see bubbles when you're blowing like bubbles into your water with a straw, that's not a surprise that there's gas in that water because there was gas already, it was just in your mouth. Not a surprise, not a new substance. Same if you take a handful of sand and toss it in water. That's not a precipitate. Now, if you took 2 clear beakers full of liquid, poured them together, and then you get this brown chunky stuff at the bottom, that's a surprise solid. That's a new substance that's being formed. So that is a chemical change. Heat and light being released. A lot of people think that boiling water is a chemical change because it's getting hotter, that heat is being released, and there's bubbles, and that's not. Boiling and melting and all of those things do not change things chemically. It's just changing them physically. Like those molecules that we drew earlier in those boxes, the difference between solids, liquids, and gases is just how far apart those molecules are, how fast they're moving. That's the only difference. The heat that you're observing when that water is boiling is coming from the stove. It's not surprising that heat plus water makes hot water. So keep an eye out for all of these changes and these indicators, but also make sure you're thinking about them and that it's a surprise substance being made, and that's the newness of it. It's not just there already. Now, this is where we get to practice identifying physical and chemical changes, and I'm going to do the first 3 with you, and then you'll do the last 3. So, breaking a pencil. Well, let's go through our indicators. I didn't make a new gas, didn't make a new solid, no precipitate, no heat or light was released when I broke that pencil, and there's no color change. All of those colors were still there. So this is going to be physical. Water freezing and forming ice. You might think, you're forming ice, that's our new substance. But remember, the only difference between the water and the ice, that liquid and that solid, is how far apart the particles are. It's still H2O, no matter what state of matter it's in. So this is physical. And once again, no bubbles, no solid precipitate, no heat or light being released, and no color change. Frying an egg. Oh wait, I just talked about color change. Doesn't the color of our egg change? The kind of outer part goes from clear to white. Even that middle yolk is still yellow, but it's a different yellow once it's cooked. So this is a chemical change, and if you think about it, you're also actually producing gases. That's why you can smell the egg cooking, because it's getting to those gases are getting to your nose. And there's actually the solidifying of that egg is actually those proteins precipitating out. And so it's going from a liquid to a solid. So I did those first 3 for you and with you, and hopefully demonstrated what I expect from you. But I need you to finish out these next 3, and we'll talk about them in class and answer any questions you have about them. So, next idea is the law of conservation of mass, which tells us mass is never created or destroyed in a chemical reaction or really anywhere else. Now, this has very big, complicated kind of repercussions for the rest of our class, but on the simplest level, we can use the law of conservation of mass with a chemical reaction. if I have this reaction and I have mercury 2 oxide being heated and it breaks down into mercury and oxygen, this one thing breaks down into 2 products. Well, as long as I know how much stuff I started with, 216 grams of that mercury 2 oxide, when I do this reaction and it breaks down, I'm going to isolate mercury, and let's say I isolated 200 grams of mercury. For some reason, I could not capture and weigh the oxygen that was produced. It didn't want to stay on the scale, so I don't know, actually, just from my measurements, how much oxygen was created, but I can figure it out, because the law of conservation of mass tells us that the amount of mass, every single atom that's over here before the reaction, before that arrow, is still going to be there after the arrow, no matter how many pieces it breaks up into. So, if I started with 216 grams and I see 200 grams there, then it must be 16 grams of oxygen that were produced. So, useful information in the lab for sure, and this is going to show up a couple other ways in our curriculum this year. Moving right along, we've got some definitions to fill in. A lot of these are going to sound familiar. You probably heard them in middle school, but we're going to go over them and make sure, once again, that we're all on the same page. So, pure substances are substances that cannot be separated or broken down by ordinary physical means. So you can't pick them apart, can't separate what's in them just with your hands or normal stuff around the house. Elements are special pure substances. These are pure substances that can't be separated by physical or chemical means. There is no way for you to break down an element. You cannot do it. I mean, okay, we do have nuclear reactions where we can split an atom, but you can't do that physically or chemically. Normal, ordinary means. Can't do it. Element is as basic as they come. There are building blocks. Compounds, on the other hand, are 2 or more different elements that combine chemically, and because they've been combined chemically, they can be separated chemically. Elements are things that you've seen on that periodic table. I know we've studied them so far. Separate elements, notice they only have 1 capital letter in each of them. Once that becomes a compound, rewrite those 2 elements together. And this compound has 2 capitals. That's one way you can always pick out your compounds. You can write a formula for them, but there's more than 1 element in them. Elements are real easy to pick out because they have to be on that periodic table. Mixtures are not pure. Mixtures are combinations of 2 or more substances, and this is important. They retain their individual properties. They haven't been chemically changed when they've been mixed, and so they're each still that separate thing, they just happen to be together. Heterogeneous mixtures are mixtures that are not smoothly blended. These are our chunky mixtures. Homogeneous mixtures have uniform composition, which means they look the same throughout. Now don't get tripped up here. Homogeneous mixtures are still mixtures. There's still different stuff there. It's just that you can't tell the difference. Solutions are just another special word for homogeneous mixtures, and even though we are going to study solutions later on, those are mostly liquid solutions, and I just kind of wanted to mention solutions can be solids, liquids, or gases. The air is a solution, and there's different gases in the air, so it's a mixture, but since you can't see it, it's a homogeneous mixture, aka solution. Now, what's the difference between heterogeneous and homogeneous? We said it really came down to how well it's mixed and how big those chunks are. But what I would probably write is, if you can see the separate substances, then it's hetero. Now, 3 examples of each. I do want you to think about some of these. Think about things that are mixed together. And then think, can I see that separate stuff that's mixed together or not? So make a little T-chart or just make a little list. But I want to see 3 examples of homogeneous mixtures and 3 examples of heterogeneous mixtures. Let's see what you can come up with. Now, the alloy is a mixture of metals with another element. And usually it's 2 metals together, but oftentimes carbon gets mixed in with things like iron to make a better, stronger alloy, which we call steel. And we do that to combine the best properties of each of those elements. So it's kind of a compromise, but only the good compromises really become alloys, things that improve the properties. And 2 examples. One is brass, which is used in doorknobs, keys, instruments, like band instruments, all of those golden looking instruments or your golden doorknob, I guarantee there is not a single atom of gold in your doorknob. Not anywhere, in the world did anyone decide, oh, I want a golden doorknob. That's the best use of my gold. If it looks like it's gold, it's brass. Silver and gold jewelry also is not 100% gold. I'm not saying that it's not gold at all. There probably is some gold in your gold jewelry, but it's probably not 100% gold because gold is too soft to last. It's going to get scratched and dented and broken real easily. So they combine it with other metals to make it stronger. Plus then, if you don't have to use as much gold to make your jewelry, then it isn't as expensive. So, makes it cheaper and stronger. Best of both worlds. Now, 4 methods of separating mixtures. You see these 4 here, and we're actually going to take a little trip and look at each of them separately. We're not going to focus on all of these, but your next lab is a separating mixtures lab. So I would definitely do a little bit of research into these 4 ways of separating mixtures when you do get assigned that lab. So, decantation. You're getting solid out of decan. So you're pouring the liquid off a solid. You might have done this at the beach if you had a muddy water or sandy water at the beach, or if you had a can of beans or tomatoes and you had to drain it for your recipe, you probably just poured the liquid off the top and the solid just kind of stayed at the bottom. Distillation is a little bit more complicated. This separates liquids by boiling points. Basically, we have substance A that boils down here, substance B that boils at this higher temperature up here, and if we heat it up so that we're right in between those 2 temperatures, then A will boil off and go away, and then B will still be left behind. So you can separate mixed liquids. It just takes a whole lot of effort. You can see this is a little more complicated than decanting. Chromatography we're really not going to study at all, but this is a good example of ink being separated. You can see those different colors coming out, and it's just that different colors, different molecules had a different attraction for these different solvents in the paper there. So helps us separate. And then filtration uses a special paper to separate solids from liquids, and it's just solid stuff can't make it through the paper, the liquid stuff can fit, so it goes through. So those are our methods of separating mixtures. You might have noticed that filtration separates solids from liquids just like decanting, but filtration separates a lot better than decanting does. So, separates the same type of stuff, but it's not the same process. Okay, we're almost there, I promise. Last 2 questions. How many naturally occurring elements are there on Earth? The answer to that is 90. Technically, that's elements 1 through 92. But because there's a couple of man-made elements in that section, the number of them is 90. But everything up through uranium are naturally occurring elements. And if you do get here and have a chance, I have a pretty cool periodic table in the room that shows the different states of matter and whether or not they're man-made elements. And so there's some white and black outlined elements on my periodic table, and those are the ones that are man-made. So kind of just fun fact there. And then, how are elements and compounds similar and different? Well, that's something that we already technically talked about at the bottom of page 6 in that pure substances section. So hopefully you can answer that, especially with a couple of those hints that I just gave you. But make sure you finish out that question there. And to finish out our podcast is to draw the matter flow chart into your packet. This is all the same words that we've just defined and talked about. This is just reminding you about how they relate to each other. So, if it can be physically separated, then that means that there's different stuff there. If uniform composition is how does it all look the same? Copy this down because we are going to be having you practice classifying next class period. Okay? Awesome. One more thing. Sorry, of course, I always forget one thing. But down here underneath, it'd be awesome if you could write a couple examples because that'll help you tell the difference later on, help the rest of this information stick. Okay, I promise that's it. This is much shorter than my last version. You're welcome. And I'm sorry, still. Bye.